Welcome to the presentation on chemical reactions. This will cover Chapter 8, and specifically in this presentation it will cover half of Section 1. Section 1, there are two main topics, and I think each topic is enough to where it should warrant its own presentation. So the presentation itself does not take an inordinate amount of time. So I'm just going to call this part 1. Section 1 will continue in part 2, where we develop the skills of balancing chemical equations. Part 3 will actually cover Chapter 8, Section 2. Sorry for the offset numbers there. But that's a relatively concise discussion on the types of chemical reactions out there. And then a lengthier discussion in part 4 of the chapter, or part 4 of the presentation, which will cover section 3, and that is on prediction. And I'm going to take you, as best I can, using this format, I'm going to take you beyond what the book does as far as the ability to hopefully develop a skill to predict products in chemical reactions. And so that's the goal. That is the goal, certainly. But the goal for this is to actually introduce chemical reactions, and specifically chemical equations that on paper actually represent chemical reactions that happen in nature and artificially in a test tube. Okay, here is an outline for the chapter, and we'll start off today with equation basics. We'll talk about evidence for chemical reactions. And see, I don't know if we covered types of equations. This actually may be out of order. But we will talk today about symbols used in equations. Otherwise, in part 2, we'll talk about balancing equations and the law of conservation of mass, locum. I believe we will end up skipping energy and chemical reactions. We may mention just a little bit of it, but I had a longer part of that presentation that I will be eliminating, so I may mention, but we won't dwell on it. And that is outside of the chapter, by the way. So just, and I'll make you aware of that at the time if it comes up. In section 2, we'll talk about the 4 reaction types. And in the last part of the presentation set, we will look into predicting products of chemical reactions. And indeed, actually, this is in order now that I see it, because, and I have a pen activated here. So types of equations, I misread that. I think I said types of reactions. So types of equations is, I believe, today. And then 4 types of reactions, that's a separate thing altogether, and that's in some other section. So I believe, yeah, that is an outline, and that is in order, and more or less it goes along with your book. Okay, we are not doing a student learning map for this particular chapter, but this the unit essential question on the student learning map will actually probably make an appearance on the Chapter 8 test. This would be the section 1 lesson question. You can certainly pause and read that. And here are the objectives for section 1. As I look down through these objectives, I do not see anything that has a star beside it or an asterisk. So I believe that this all comes directly out of your book. Understanding when a chemical reaction has taken place based on evidence. Looking at the components of a correctly written equation and identifying them. Understand how to write a word or a formula equation or a chemical equation for a chemical reaction, and then create a correctly balanced chemical equation, which would be something that we'll do beyond this presentation, part 1. That'll be more part 2. Okay, so what is a chemical reaction? If we are going to be talking chemical reactions, it's kind of nice to know what they are. Very much like when we were in Chapter 6, bonding. What is a chemical bond? That's a very important question if you're going to have a whole chapter or a whole unit on it. Okay, well, here this is. It is any process by which one or more substances are changed into one or more new substances. The new substance will... Let's say that again. The new substances will have unique characteristics all of their own and will be very different from the substances they were created from. So consider water being created from hydrogen and oxygen. What is hydrogen? Hydrogen is an explosive, highly flammable gas at room temperature. And oxygen is an invisible gas, of course necessary for life, but it supports flame. You put these together chemically and we get water. It's explosive actually, but when you cool it down, you get liquid water. And think about liquid water. It puts out lots of flames. It's not explosive at all. You can't breathe it certainly. So water is very different from what it is made of. And so therefore that is a very good, even albeit a simple example of a chemical reaction. Okay, what about evidence for chemical reaction? If you were seeing something in a test tube happening, what could we actually witness and say, ah, here we go, it's a chemical reaction? Well, I think I have my pen activated. You could have evolution of heat or light, which would indicate exothermic. So heat is given off, the test tube heats up, something like that, all on its own. Light. Now, when would light be emitted from something? Well, think about this. July 4th. You're wandering around Corning or Wellsboro or maybe even anywhere where they're going to do fireworks. You have vendors. Those vendors are selling lots of stuff, soda pop, popcorn, whatever, but many of them have glow sticks, all kinds of glow sticks, necklaces and batons and all kinds of things, hula hoops. Well, we take those glow sticks. If they're not already activated, you basically break an ampule on the inside of the plastic by bending the plastic back and forth a little. You release a chemical, you shake it, and then it lights up. And it'll stay lit up for anywhere from 4 hours to 24 hours, depending on the chemical mixtures. And so that's light. That is light without heat. It doesn't heat up. And chances are most of that is non-toxic, but I wouldn't trust it personally, so I'm not going to eat it. But that's where you could get light emanated without heat, otherwise heat. It's a chemical reaction. You could have instead the absorption of heat. That would be endothermic. You could have the production of a gas where you may see bubbles actively coming out of a chemical reaction, or maybe some wisps of what you might think of as smoke, but is some sort of a gas, maybe or maybe not steam. Steam is actually really a word used for water vapor, and it may not be water vapor. Formation of what is called a precipitate, normally symbolized PPT, because that's such a long word that chemists just dread having to write it out, and so they use PPT as an abbreviation. What is that? Well, it's basically an insoluble product, meaning a solid that is formed in a liquid environment. So consider this reaction here. We have a liquid being poured into another liquid. As the liquids meet, a precipitate forms because the solid that forms cannot dissolve in any of the solutions that are there because it's a brand new substance. So the formation of a precipitate. Now some of them are not this dramatic. This happens to actually have lead in it, and because it's I think a lead nitrate, that it is a very bright yellow color, that we can't do that anymore because of the lead content in at least one of the chemicals that makes that happen. But it's a really dramatic example of a chemical reaction with a precipitate, and you can probably YouTube that one and see the video on how that's made. It's really cool. Color change. So is there a color change in your substance? Is there an odor change where you had no odor, now you have an odor? You had an odor and now you don't. You have an odor and now it's different. Of course, smelling something in a chemistry lab, if you can avoid it, is always a good thing. You should never smell anything directly. But every once in a while, it's something you notice. And every once in a while, there are labs where you actually intentionally need to check the odor of something. Also, the appearance or texture change. Something like an iron nail that rusts or a steel nail that rusts, that's a texture change and an appearance change. There is a link here that if you are able to search the internet, you could actually look up a couple of different videos on evidence for chemical reactions, and this one looks like it's in 2 parts. Okay, a chemical equation, what is that? Well, it simply represents a reaction, very much like a recipe represents how to cook something. A chemical equation is kind of like how chemistry is done in shorthand form. And so I like it, as anything that's short, lazy chemists. How short, how small, how minimal can we make it to represent something greater? So it's just kind of an amazing skill set, right? So here we have chemical equations. What are they? Well, they represent by symbols and formulas the identities and the relative amounts of reactants and products involved in a chemical reaction. Reactants are anything, like consider down here, anything you start with. And anything you start with, we simply call reactants. You may have 1 reactant, you may have 100,000 reactants. It doesn't matter, whatever you have, if that's what you started with, these things are called reactants. The arrow will separate the reactants from the products. And sometimes, once in a while, we'll see maybe a double arrow, but that's okay. It's still a separator. And the arrow, at least one arrow, will always point to the right anyway. What it points to, again, one or many, these are the products. So reactants yield products. That's how you could read that. This particular example, and I won't bother to erase all the pen marks, but this particular example has a substance called ammonium dichromate. Now this is a substance that you should currently be able to write the formula for from the name, because this is in your skill set. This would actually be a type 1 compound. Produces nitrogen gas. N2 is nitrogen. Nitrogen is one of 7 what we call diatomics. So diatomics, meaning that they travel as molecules when they're in element form. So this is just pure nitrogen now, and because it's isolated chemically, it's just nitrogen, it would actually pair up with another nitrogen atom to form a molecule, and that's much more stable than a single nitrogen atom. Over here in ammonium, nitrogen can be a single nitrogen atom because it's in a compound, and the compound stabilizes it. But over here, there's no compound. Okay, then what do we have? We have chromium 3 oxide. So chromium 3 oxide is a solid. This is a precipitate. It will actually fall out of solution very much like that lead, that yellow lead compound in that picture. And then we made water. Due to the temperature, it looks like water is a gas as opposed to a liquid. If you cooled it down, this would become a liquid. So there you go. This is a chemical equation that is able to show you in shorthand form a lot of what is going on when a compound like ammonium dichromate actually breaks down. This is what that reaction actually does. Okay, well, reactants and products, just a little bit more focus here. Reactants are the starting material in a chemical reaction. The reactants are always written to the left of an arrow in the equation, even if it's a double arrow. Products are the ending materials in a chemical reaction, and they are always written to the right of an arrow. Even if it's a double arrow, one arrow will always point right, and the products are always on the right. The arrow itself actually simply means to produce or to yield, but never say equals. Okay, that's bad because that's kind of like a math thing. And that would be like in the previous example where it said ammonium dichromate produces, will decompose to produce nitrogen and the others. And if you said, well, ammonium dichromate will equal the others. Well, that's not really correct, even though I know what you mean if you said that to me. That would be like saying I have a brownie mix out of a box, I have an egg to go with it, and a cup of oil. This will equal brownies. No, it will not. It will produce brownies, but it doesn't equal brownies. And I think we would all agree to that. Chemistry, exactly the same as far as the usage of the words. So never use the word equals. Produce or yield, great words to use. Okay, there are 3 types of equations that I would like you to be aware of, and on this slide I'm actually starting with the word description, and a description is not an equation. That would be like me talking to you as I have done the whole time here, and if I described a chemical reaction to you like that dichromate one. That's just a description. It could be like verbal here. It could be written down somewhere. And I can mention the products and the reactants in any order, like the brownie mix thing. If I take a brownie mix, I can make brownies, but I will need oil and an egg. Well, the brownie mix, the oil and the egg are actually the starting material. They are your reactants, if you will, and the brownies are your product. But I mentioned the brownies not at the end of that sentence, but right almost close to the beginning. Brownies can be made from, or if I start with a brownie mix, I can make brownies, but I need. So be very careful if you have a description, because you have to sort out what are the reactants and what are the products. So that's something that you have to want to just kind of ferret out. Otherwise, if, number 1 here, if we have a word equation, or if you have to produce a word equation, what is that? Well, a word equation is just what it says. It will use the names of the substances, and it will use symbols. So an example of that would be making water. Here I have the name hydrogen, it's a gas, plus, meaning we're just going to combine these together, oxygen as a gas will produce water as a gas. So I'm using symbols, G plus, G, arrow, G, and I'm using the names. This is a word equation. You don't have to get any fancier than this with word equations. You know, there's nothing more really to do with them. Let's go on and see the other two. Okay, the other two types of equations often look very, very similar to each other. So, from a word equation, we may want to go and develop a formula equation. What's that? Well, you simply replace the words, the names, with formulas. So, formulas for all substances are actually used using standard equation symbols. So, formula equations don't have to be balanced. Actually, they never are balanced. So, I'll tell you about what that means in a minute. So, let's check it out here. Here is hydrogen right here. Hydrogen, I wrote H2 because it is one of the 7, like nitrogen, it is one of the 7 diatomic molecules. Oxygen is also one of the 7. In fact, I'll come over here and list them, right? So, diatomic. That would be hydrogen when it's alone. Even though it's in an equation over here, it's actually alone. It's an element. Nitrogen, oxygen, and then the halogens fluorine, chlorine, bromine, and iodine. All of those travel, when they're in element form, they travel as molecules for stability. So they'll covalently bond with each other and they will travel that way stably. And so when you see them in equations like this, where hydrogen is by itself and oxygen is by itself, then we have to write them as molecules. In a compound, they don't have to be molecules because now we have a compound that will help stabilize itself. And so the reason why there are 2 hydrogens there is not because it's diatomic, but because of oxygen and valence electrons. So that's a whole different thing, and we talked about all of that in Chapter 6. And you can go back and view the Chapter 6 material. All right, so let me erase a little bit of this just to clean it up. Okay, so a formula equation, we have hydrogen combining with oxygen to produce water. The formulas are all there, and excuse me, they are all correct. But this is not balanced. What does that mean by not balanced? Well, let's count our atoms. Over here, I have 2 hydrogens sitting right there, and I have 2 oxygens sitting here. When they combine together, I have 2 hydrogens in water, but only 1 oxygen in water. Where did my 1 missing oxygen go? Well, in a formula equation, it doesn't matter. I'm not worried about accounting for all of the elements, all of the atoms rather. As long as all the elements are there and all the formulas are correct, I don't have to worry about that. So that's a formula equation. However, if the numbers do not match up, like they did not in this one, that we might want to go and then put a fully fledged chemical equation together, which is actually physically balanced. Now, balancing, we would then do this. We're going to use a multiplier. Think about this, okay? So, let me erase this, and I'll actually work one up here with you, because I know you can already see that answer. But how did I get that answer? Here's how I got it. I have 2 hydrogens on the left, separated by an arrow, and I have 2 hydrogens on the right. So they're okay right now. I have 2 oxygens on the left, and on the right, I only have 1 oxygen. Now, I can only make more of them. I can't take things away. So if the formulas are correct, I have to make more. Well, what can I do? Well, I can actually multiply by a water molecule by 2. So that would be like 2 times. Now, it's not really, you don't put a multiplication sign there, but you multiply it by 2. So that 2 is actually called a coefficient. And that 2 multiplies this to make 2 water groups. If I drew them, there's 1 water, there's the second water. So now I have 2 oxygens, which is right here and right there. Now that I have 2 oxygens, my oxygens actually are in balance. But I did actually affect the hydrogen, because now I have 2 times 2. I have 1, 2, 3, 4 hydrogen, but I only had 2 on the left when I started. So what I could do is I can simply double that amount to make 4. And so now that I have 4 hydrogens and 2 oxygens, I have 4 and 2 respectively over here. And so this thing balances, and that's what you see down below. 2 hydrogen molecules combining with a single, if there's no number, you can assume it's a 1. A single oxygen molecule produces 2 water molecules. And when nature, or when we make water using this formula, we always make oxygen or make water molecules in pairs. So it's always an even number of water molecules that are actually made because of this particular equation. We can make water through other ways where you don't have to have hydrogens and oxygens in this format, but that's the way it is. Let's move on. Okay, diatomics and polyatomics. We are halfway there. Diatomics and polyatomics. When converting a word, I'm up here. When converting a word to a formula equation, remember to keep track of diatomic elements. Because if you're going from a word equation, you have to come up with your own formulas. And so if you have to come up with your own formulas, that means that you have to then remember, oh yeah, hydrogen, I better make it diatomic. Oh, oxygen, I better make it diatomic. So here's a list again of all the diatomics. And these are, by the way, on your ion list, that handout from Chapter 7. Now, we also actually include, chemistry in college includes these, that we have sulfur, which actually, the atoms of sulfur clump together in groupings of 8 instead of being diatomic like chlorine up here, right? So sulfur actually clumps together in atoms of 8 for stability. Phosphorus clumps together in 4, and I believe arsenic, the element, also clumps together as 4 atoms of arsenic, which is much more stable than a single atom of arsenic, which really does, it just, you can't isolate it. And we have to remember this if you are mentioning, like, you know, sulfur combines with you know, phosphorus, you know, I would have to write S8 down here. And for phosphorus, I'd have to write P4. I can't just write S and P. That's how the diatomics would work. Equation specifics. Okay, let's talk a little bit about equations. There are many symbols that are used in equations, very much like in cooking. There are all kinds of abbreviations for teaspoon, tablespoon, cup, pint, ounce, things like that. And so with equations, we have our own symbols in chemistry. Well, it's in science. I mean, chemistry uses it, but it's really all of science. Well, one common one is a lowercase s in parentheses. And in parentheses, right, this is going to represent anything in the solid phase. So anything with an S after it in parentheses would be solid phase. Less used these days, but it used to be used a lot more. And I have some really old textbooks from like 50, 60, you know, 80, 100 years ago. And they sometimes use a CR instead of an S in their equations. And the CR simply meant that it's a crystal. That's all that actually means. Now, we still know they're crystals, but chemists have actually kind of generalized that one a little bit more just to call them solids at this point. A very common one that we will see is an L. It's a lowercase l, and that would represent anything in the liquid phase. I personally, you know, if you write an L just like a, to me that almost looks like a capital I, and it could be. And so I actually, when I'm handwriting, I use a cursive L. Like a handwritten L with the loop. And that's why I wrote it or typed it with the L as a loop here, italicized, just to make it stand out differently from like maybe a Roman numeral 1 parentheses if you're talking about a type 2 compound. So I like the lowercase loopy L just because I think it stands out a little bit better. Use what you want as long as it's in context. One common one is a G in parentheses. It's a lowercase and it means gas, anything in the gas phase. One other common one that you see very often is AQ. AQ stands for aqueous. And aqueous means that it has been dissolved, typically in water, but every once in a while I'll see aqueous used a little bit for something else, you know, maybe dissolved in vegetable oil or something. But they would like say, like AQ oil or something like that. They'd kind of make a little notation of it. It's not really water here, it's oil or it's gasoline or it's benzene or it's something else. But those are very, very common symbols in chemical equations that you would want to know what they mean. There is a symbol that is used right here. It's a Greek letter delta. I believe it's an uppercase, as a matter of fact. And when you see this, typically it's above an arrow. And when it's above an arrow, it simply means that you need to heat it up. That could be from a Bunsen burner, an oven, an open flame of some sort, any heat source that would be required. But that Greek letter delta written above an arrow is just meaning that you got to heat it up. Once in a while, you will see these symbols, an up arrow or a down arrow, and they are only used when it's a product. So you only ever see these to the right of the right of the horizontal arrow. And what they mean is this: the up arrow, so right up here, the up pointing arrow would simply mean that they expect the substance when it's created to be a gas, and you may see active bubbling. So it's kind of like a physical reminder, hey, look for bubbling here because it's going to be a gas. And so if I said this will produce H2, and I use the arrow, I'm going to expect to see bubbles actively in my solution somehow. That's what I'm going to look for. Likewise, with the down arrow, it's exactly the opposite. It's when you expect to see a solid present. So like that substance, I believe it's going to be PbI2, that yellow substance you saw in that beaker, that the two clear liquids were pouring together. So with that lead 2 iodide, I might use that arrow instead of saying PbI2 solid. Either one of those is fine, but this one simply means, wow, you're going to see the precipitate. You're going to see the solid form because it will be a product. So you see those. Not as often, and probably maybe more with labs, because of course labs you're actively doing things. Boy, I miss labs too. Miss you kids, miss being in class, miss labs. Other symbols, just really quickly here, once in a while we'll have catalysts present, and we use that, like above and below the arrow where you have reactants and you have products form. The area above the area below the arrow, these are very versatile areas where we can put a lot of information, and if we need more, we just make a longer arrow if necessary. But this is a great place to dump information so we can really have a thorough understanding of exactly what's going to happen in this reaction. So a catalyst, if I were to say, let me erase this cloud up here, and if I were to say, write platinum, so the element platinum, this would mean that the reactants, when they react together, will react much faster if platinum is present in the test tube. Now the platinum won't react with anything. It's just there to kind of help the reaction along. When the reaction is done and all of the products are formed, we can literally go back into the test tube and take the platinum out, put it in its own jar, and then just reuse it sometime later on, after you'd clean it up, of course. You could write a specific temperature. Instead of saying heat or the delta letter, you could put a temperature down, like 15 degrees Celsius or 221.6 degrees Fahrenheit or whatever. So, it's just you could write a temperature instead. Once in a while, you could write a pressure like 1.2 atmospheres, which is slightly more than typical air pressure that we would experience. Your ears may hurt in 1.2 atmospheres. Okay, let's move on. Okay, with all chemical equations, because we will have to write them, remember and this is chemical common sense, but it may not be kind of practical common sense for us. We always, if we know it and we know it's true, we want to write it down. Never omit information if you know it for a chemical reaction. So represent all known facts about the reaction. So if you know it's a solid, write a solid down. If you know it's a liquid, write a liquid down. If you know hydrogen is present, make sure hydrogen is written down. We must have correct formulas. So you can't write H down if it's hydrogen gas. You have to write H2 because H is incorrect. So correct formula. If it's aluminum nitrate, you can't just write down AlNO3. You would have to write AlNO3. Why? Well, because aluminum is a 3+, nitrate is a 1-, and you would have had to crisscross. And so that formula, not the other. And lastly, which is what our second part of our presentation is going to entail, locum, law of conservation of mass, must be satisfied. the number of atoms, the type of atoms, meaning if it's hydrogen, you gotta find hydrogen has to be a product if it's a reactant. The number and the type of atoms for reactants and products must equal, and when they do, by a balanced chemical equation, we have satisfied locum on paper, because nature never loses anything. And so if nature accounts for it, we have to account for it on paper. Okay, let's move on. Also, with the characteristics of chemical equations, not only is locum needing to be satisfied on paper because nature never loses anything, how we satisfy locum, how we balance equation, is by using these things called coefficients, which are numbers, just small whole numbers always. We're not allowed to use decimals or anything like that. Small whole numbers that will appear in front of a substance, which will increase by multiplying. It'll increase the number of atoms in that substance, and this allows the reactants and the products to balance out to be equal in numbers, even though, of course, they have been rearranged. Coefficients, remember, are multipliers, and coefficients of 1 can be assumed and do not need to be written. Here's an example. Example is just water. So in water, I have a coefficient of 2 for the hydrogen, so that makes 4 hydrogen atoms, 2 molecules. We have nothing under the or with the oxygen, so that is assumed to be a coefficient of 1. And so you don't have to write it. You can write them. It's okay. You don't have to. I don't, because chemists don't, but you can write it. It's okay. And then a coefficient of 2 for waters, and we already did the multiplication there. And this happens to also say plus energy, because I know that when water forms, it's actually explosive, and so it gives off a lot of energy. It's very dangerous. It's what happened to the Hindenburg, the big blimp, back in 1937. That was a reaction that made a lot of water eventually. Now, final coefficients. Final coefficients are useful to show relative mole amounts. We do mole conversions. Well, this actually tells us mole amounts. So this could tell us that 2 moles of hydrogen will combine with 1 mole of oxygen, and that will make 2 moles of water vapor. Now, we balance by the particle. This is really thinking about 2 molecules of hydrogen and 1 molecule of oxygen to make 2 molecules of water. We balance by the particle, but it's neat that final coefficients can actually also include bigger numbers, because we know a mole is Avogadro's number of these, so that's 602 sextillion of these molecules, but that's a mole of it. And so it's neat that we can draw that relationship there, because that allows us to then start doing like mass experiments where we can actually weigh things out in the lab. Okay, next up, so this is the last slide today, or not today rather, but with this presentation. Section 1 will continue with part 2, and because I had to break section 1 up, and that will cover then balancing equations. This is a very important skill, and so I suggest that you read the chapter, read that section prior to viewing the next presentation, so you're familiar with the bonding process. I think you'll get a lot more out of it, and in truth, maybe if you're getting it well, you can skip ahead a little bit and say, you know, I don't need this slide, I don't need that slide, maybe I can skip ahead, just look at it really quick, see if the presentation makes sense, and then move on and maybe not listen to me, you know, for 4 minutes go on about the same slide. I strongly recommend that. And you put the two together, and wow, you really hopefully have a solid bit of information. And don't forget, YouTube, not just my videos, because any videos like this I try and load onto YouTube just in case you prefer that format, but chemical videos like the Tyler DeWitt dude, the Professor Dave dude, the Mr. Anderson dude, and the Khan Academy, which I got this idea of writing on slides for, and the Organic Chemistry Tutor, and these are 5 of probably 1,000,005 out there of educational chemistry video people. Really look for this stuff, and especially something like balancing equations. You may struggle a little bit. You know what? millions upon millions of other chemistry students in high school have struggled with balancing. So there are like tons of videos out there, some better, some worse, but there are tons of videos out there that say, hey, here is how you balance chemical equations, and they'll take you step by step to get them to actually balance. And so I really strongly suggest that that's what you do. Okay, this is it for part 1, and I will be with you again in part 2 where we actually talk about balancing, and I'll have the pen going again, and I'll actually balance some equations and talk you through it, and then we'll move on from there. Thank you.